right, good. Thanks for watching, everybody. Thanks for either tuning in or watching this on the PSI YouTube channel. And I just want to give basically what is just a status update on my current lunar data analysis program grant, purpose-driven lunar geologic mapping. And I want to first acknowledge, see if I can advance my slides. Yeah, if I can acknowledge my co-authors and my collaborators on this, Ben Greenhagen and Deborah Buchkowski at Johns Hopkins APL, Harry Heisinger and Carolyn Vanderbogert at University of Münster in Germany, and then Noah Petro and Dan Moriarty at NASA Goddard. So this is a collaborative effort between the 7 of us. And I don't think this talk will be super long. Like I said, it's mostly a status update, what I'm up to. But the overall outline of my talk is I'm going to talk briefly about 4 billion years worth of impact records on the Earth and the Moon. I'm going to talk about large lunar basins, determining the age from impact melt from large lunar basins. And then I'm going to talk about the geologic mapping for future missions to determine the age date, where the context is really super important for interpreting geology. So as I've talked about before, and as does get talked about, the moon is the only planetary body at 1 astronomical unit from the sun where there's a preserved geologic record of over 4 billion years worth of impact cratering. Earth is also at 1 astronomical unit from the sun, but its impact cratering record has largely been erased. Most of Earth's surface rocks are less than 700 million years old, and most of the moon's surface rocks are older than about 3 or 3.5 billion years old. So they have different and complementary geologic records. And so if we wanted to understand the impact cratering record on early Earth, really the only place in the entire solar system where that record even has a proxy indicator is on Earth's moon. This is some work that I've published on before in the Planetary Science Journal and in JGR Planets. And this is work that I've continued with a now funded LDAP grant from NASA headquarters. So one of the big outstanding questions in not just solar system science and planetary science, but really lunar science is whether or not, well, really it has to do with the impactor flux in the early solar system, where the impactor flux is really, you can think of it as late stage accretion as asteroids and meteoroids continue to get swept up on into planet or planetary-like bodies. And so if we plot this back going 4.5 billion years, and the impactor flux is really high, did the impactor flux slowly decline with time to the low background that it is today? Was there this huge flux of all of a sudden we had a cataclysmic event of impactors happen around 3.9 billion years ago, or was it higher then and then fall off a cliff? We're not sure. What led us to believe that there might have been a spike at 3.9 billion years was that a lot of rocks collected by the Apollo astronauts on the moon tended to cluster around 3.9 billion years. But later geologic analysis seems to indicate that really they were dating the impact of one large basin forming event over and over again, namely the Imbrium basin forming impact, which is a roughly 900 or 1,000 kilometer diameter basin on the near side. So my why might we care about this? Among other things is, life emerged on Earth, we think about 3.8 to 4 billion years ago. And if we want to understand the geologic environmental conditions at the time of abiogenesis, that is when geochemistry evolved into biochemistry, we really need to understand the impactor environment. And again, the only way to really do that for Earth is to study rocks on the moon. Now, of course, when a meteoroid hits a planetary surface, it generates a lot of heat. In fact, it vaporizes and melts a large quantity of that target rock. And when that target rock cools, it locks, and the radioactive elements in there lock in the time of formation. And so if you go collect a cooled sample of impact melt deposit and you do various radioisotope age determination studies on it, like with uranium lead or lead less or potassium argon dating, you can derive the age at which it crystallized and therefore how long ago it was melted and thus the time of the impact. So a lot of large lunar basins, the entire interior of them at one point would have been an impact melt sea. And so the trick is just to go to, quote unquote, just go to where the impact melt sea was. The problem is that most of these basins are really old. The original impact melt deposits have been obscured by subsequent impacting events, subsequent volcanism, and just the general churning, the regolith gardening from meteoroid bombardment of the top several meters of the moon's surface. And so one way to get at freshly exhumed impact melt deposit on impact basins is to go to the central peaks and rims of superposing craters that can that would have relatively gently brought up impact melt deposits from their underlying basins. And hopefully the shocks and the heating from the formation of the smaller craters would not have reset all of the radiogenic ages of the original impact melt deposits. So there was a slide several slides ago, I'll just flip back to it really quick, where there's a lot of circles drawn. Really, it's basins larger than about 400 kilometers in diameter that I'm interested in locating areas where future missions could sample that cooled impact melt deposit. And so there's roughly 42 of these basins that have been identified on the moon that are 400 kilometers in diameter and larger, and figuring out the spacing and time and the timing statistics of the formation of these large basins would be a proxy record for Earth. And so I have selected a subset of those large basins to do geologic mapping, detailed geologic mapping, and try to identify places where future missions could sample those. So one of the basins that I have elected to do, and there's all these basins, so you just got to dive in and just start doing it. No strong reason why I chose Grimaldi over others, except that there hasn't been a ton of work done on this, and I thought it'd be fun to dive into a lesser well-known or studied basin. Grimaldi Basin is on the far western hemisphere of the lunar near side. It is a peak ring basin, but most of its rim and peak ring have been obliterated by subsequent impacts and emplacement of ejecta. So here's Grimaldi. If you can see my cursor, it's been filled with a fair bit of Mare basalt volcanism. The western edge of Oceanus Procellarum is shown right in here. So these are thin, these are Mare basalts that thin as they move westward. There's a few superposing basins like Riccioli and Hevelius basins have slightly superimposed the rim, but where the rim of Grimaldi, I kind of interpret it is this right out here, kind of continuing this arc in this direction, is interpreted as the outer rim of Grimaldi, and then the inner peak ring of it is shown by some of these mountains that are, or some of these massifs that are still visible. Now, this image is a mosaic from the Lunar Reconnaissance Orbiter wide-angle camera image taken near dawn or dusk, I'm not sure actually. But at any rate, the sun is low on the horizon and it casts really great shadows. This is not the only data set I use for base mapping, but it's one of the more convenient ones. Now, the entire moon has already been mapped, so I'm not, to first order doing anything new. The entire moon has been mapped at a scale of 1 to 5 million. This is an example of previous work. This is just a screen grab from the 1 to 5 million lunar geologic map from the commonly available website software QuickMap on Arizona State University's website. And so you can see that there's been a lot of geologic mapping done here already. However, I have gone back and I've mapped this myself using multiple data sets at a much finer scale of, instead of 1 to 5 million, I've mapped it at 1 to 200,000. And so I'll just flip back and forth between these a little bit. So 1 to 5 million, 1 to 200,000. And again, the purpose is to try to locate areas where future missions could either land or otherwise get to, where preserved impact melt from Grimaldi could be exposed near the surface. And I've basically completed the geologic mapping in this area, but I want to zoom in on a few areas and just highlight a few good areas. So I'm going to, in the next slide, I'm going to zoom into this area down here. The top left just shows a regular photo mosaic of it from the Lunar Reconnaissance Orbiter camera, wide-angle camera. And then I've shown the mapping down here. And a few things I want to point out is this really beautiful, very pronounced lobate deposit that has come in from the southwest. And to the southwest of Grimaldi is the famous Bullseye Basin, the Orientale Basin, that is the youngest and best preserved multi-ring impact basin on the moon. And in fact, Orientale is sort of a touchstone for multi-ring basins throughout the solar system because it's so well preserved. And so Orientale has covered that whole hemisphere of the moon and a lot of its ejecta flow that is still very evident on the lunar surface. And this is one of these beautiful lobate deposits of ejecta that has flowed in through a breach in the southwest portion of Grimaldi's rim. And so I've mapped it in this orange color here. We have some just cratered plains material in here. I've mapped in blue. The Mare basalt of Mare Grimaldi I've mapped here in pink. What I've mapped here in this hashed pink here is still Mare deposit, but it corresponds to these wrinkle ridges here. Normally these are mapped as like a one-dimensional linear tectonic feature, but I thought at this fine resolution, it'd be more convenient if we're making a map that can be useful for interpreting things on the ground to actually map out the plan form expression of it. What we're probably seeing is the surface expression of accommodated tectonic strain at depth, where basically we've got a thrust fault and buckling of the upper crust there. There's a smaller crater here that's also been partly embayed with Mare basalt flows. And there's quite a few normal faults and grabens crisscrossing the area here that extend through multiple units, both the Orientale lobate flows and the cratered plains here. What they do not cross, however, is the Mare in this area. Another area I want to zoom in on is this really wonderful example of lunar volcanism, of volcanoes on the moon, and specifically these pyroclastic deposits. You can see this lower reflectance material along these elongated pits, where we likely had fire fountaining at some point in the past, depositing mafic materials rich in a lot of iron and magnesium, a lot of olivine, pyroxene, and FeO, iron oxides around in here. And this is kind of towards the northeast of the region. So we've got this relatively young pyroclastic deposit with few superposing craters, some other older degraded impact craters, and we've got some tectonic fracturing going on here. So, you know, these tectonic fractures here I've mapped in blue are probably related to at least the tectonic rupturing and the buoyant ascent of magma that produced this deposit here. Excuse me. Oh, this is just a zoomed out view of that other area. Moving on, and then really where the, excuse me, I've drawn a cross section line through here, A to A prime to A double prime, and I have it going through this crater. There's quite a number of craters around where you would expect the peak ring of Grimaldi to be, that when we look at it in using compositional data, in this case from the Japanese Kaguya multiband imager that really draws out plagioclase feldspar compositions, we see these plagioclase feldspar anomalies around quite a number of these craters. And rather than mapping it as a different unit, I mapped it as this hashed overlay right around in here. And this is exactly what, you know, we would expect the original target material of Grimaldi to be. And this is probably exposing relatively fresh, and by fresh I mean whenever this crater got around to forming, fresh material that was probably in that original impact melt sea from the Grimaldi forming impact. So what I'm proposing is that if you wanted to find the age of the Grimaldi basin forming event, this crater in the northeast side of Mare Grimaldi is one of the best spots that you'd want to go pick up rocks. And so this is an Apollo astronaut. This is from Apollo 16. This is Charlie Duke picking up the rock Big Muley. Big Mulberger at the Descartes Highlands. So great spot to pick up rocks, whether you're an astronaut or a robot, and do radiometric age determination. Now, in the next slide, I show a cross-sectional interpretation that I'm mostly finishing up now. The overall geologic map is up here. I've circled this area, and just here's a cross-section going from A to A prime to A double prime, left to right across here. And we've got the basin rim, the peak ring basin. We've got the Mare basalt fill. We're inferring that there's probably some mantle uplift due to isostatic rebound of the mantle there. We've got some thrust faults at depth with the surface expression manifesting as wrinkle ridges. And we've got this pyroclastic deposit here. And this area right here corresponds to this area. Again, probably a pretty great spot to get original and dateable Grimaldi impact melt deposits. So I'm basically finished with Grimaldi, pending a little bit more detailed compositional interpretation from members of my team, especially Dan Moriarty and Ben Greenhagen, and that may inform a few tweaks to this map, but I don't expect it to change a whole lot. I'm moving on to another basin now, and that is the archetype for all multi-ring basins in the solar system. And this is just a screenshot from ArcGIS Pro, where I'm doing the work of a dawn mosaic of Orientale Basin. I'm starting to map the Mare deposits, the fractures. I'm starting to look at the compositional anomalies and ejecta from this is Maunder crater right here. Orientale is great because you can land anywhere in here and you're looking at really pristine impact melt from the Orientale forming impact. And so Orientale is a really great spot to test hypotheses for the best place to sample impact melt. So even though Orientale, it's a no-brainer where to go to sample impact melt, I'm looking at other craters like this little guy right here that could be exposing exhumed impact melt from depth and as a good and giving us confidence that we know what we're doing when we would go to other basins to look at them for impact melt. So the conclusions at this point is we're starting to find good locations in Grimaldi Basin where the high resolution geologic mapping is nearly complete. And we're moving on to other basins around the moon to inform where we can go to learn about the early cratering record of the moon and therefore early Earth. So thanks so much for your interest and attention.
Awesome. Thank you so much. I have no questions. Beatrice, do you have any questions? Are you around?
I'm around, but I'm not a lunar person, but that was very interesting. So what's next for you? I can ask that.
Sure. Well, I've got one basin down. I've got about 7 or 8 more to go, at least that I propose to do in my proposal. So like I said, I've already started mapping Orientale, but then I'm going to go on to some other basins like Nectaris, Moscoviense, and do some high resolution mapping around there and try to find future landing site candidates for future missions. And so, and then start, writing the paper on this topic. And I really like this. So, once that paper is underway, I'll probably write another grant proposal to keep doing more of this around the moon. And, as more of these private missions go to the moon, the CLPS landers, the commercial lunar payload services, and as Artemis astronauts return to the moon and we bring back more samples and we'll be in kind of a golden era of lunar science again. And so we'll be in a much more data rich environment, and, we'll see how that changes where we want to take geologic mapping and how that informs how we do age determination for other basins. So we're going to be, we'll get a lot more information once we start landing a lot more missions on the moon and hopefully bringing some rocks back.
So what are you using to map? Are you using any AI, or do you have your own, or stuff that's already there and then you adapt it to your needs? Or
no, I'm not using any artificial intelligence, just hopefully actual intelligence. I'm using a program called ArcGIS Pro, which is kind of an industry standard in mapping. Right. And I'm using base maps from the Lunar Reconnaissance Orbiter camera, but then using other data sets like the low angle images. I use the Lunar Orbiter Laser Altimeter Global Digital Terrain Model, and I can make shaded relief maps to help show in some shadows. I use compositional mapping information from the Kaguya multiband imager. And then others on my team are using compositional information from the Moon Mineralogy Mapper, the hyperspectral imager, infrared imager that flew on the Indian Chandrayaan-1 orbiter mission. And then we're also using Diviner radiometer mid-infrared data in like the 8 to 9 micron range to look at silicate mineralogy to complement the M-cube data sets. So combination of images and spectra and laser altimetry.
So quite a lot of data to get all into a concise picture.
Yeah, it is. And that's kind of the fun part is on the one hand, it's a lot of scientific synthesis, but then there's also an artistic component and sort of an interpretive component of what's the nugget of information we want to convey and what is the visually most compelling way to present that scientific interpretation visually on a map.
Nice.
Yeah, thank you.
All righty. Well, I'm going to go ahead and stop the recording. You feel free to keep chatting.